Hi everyone, so today we're going to be talking about logistic regression. So what is it? Logistic regression is a form of classification, not regression, and it's named that way for historical reasons. As you can see in the graph above, we have this data set, and the data points are labeled either blue or red. And so with logistic regression, we try to find the line that can separate the data points most effectively, so that if we have a new data point on this graph, we can try to guess if it's going to be blue or red. Practically, this is what classification can look like when we're trying to process an image and tell if it's a hot dog or not a hot dog. So let's see how to implement logistic regression. Let's say we want to create a logistic regression model to classify cookies as fully cooked or not cooked, based on how long they were in the oven for and what temperature of the oven it was. And so here we have a sample data set with some bake times in minutes, temperatures in Fahrenheit, and cooked values, with 1 being cooked and 0 being uncooked. So we're going to go over the hypothesis function, cost function, and gradient descent for logistic regression. In a similar fashion, we use gradient descent to optimize our model in order to get a more and more accurate predictions. So the hypothesis function we use in our model to guess whether the cookie is cooked or not is altered in this scenario. So we have h theta of x being equal to g of theta transpose dot product of x. So let's represent theta transpose dot product of x with the term z. So we can simplify this expression to h theta of x is equal to g of z. And so g of z is the sigmoid function, which as you can see here is equal to 1 over 1 plus e to the power of negative z. And this gives us a nice curve that you'll see in a graph further. So just to reiterate, theta transpose is the same as what we had for the linear regression, theta, but we just transpose the weights. So if it's a row vector, we turn it into a column vector. If it's a matrix, we transpose and flip it about the diagonal. So so the output that we get from h theta of x is always between 0 and 1, and actually never reaches 0 or 1. So in order to take this output between 0 and 1 and turn it into a binary classification, we set a threshold, let's say in this case 0.5. And so we say that whenever h theta of x is greater than 0.5, then our prediction is that y is equal to 1. And every time it's less, we predict y is equal to 0. To give you a sense of what the sigmoid function does, so we know that h theta of x is equal to g of z, and z being theta transpose dot product of x. So whenever theta transpose dot product of x is greater than 0, then the hypothesis function is going to give an output that's greater than 0.5. And so basically we can simplify to whenever the theta transpose dot product of x is greater than 0, we're going to predict 1, and otherwise we predict 0. So here is a picture of the sigmoid function, function g in our terminology. And so yeah, just reiterating, if it's greater than 0.5, we have a baked cookie, otherwise we classify it as unbaked. And the whole point of the sigmoid function is to basically map values so that you can take any input from from negative infinity to infinity and give an output that's 0 to 1. And that helps us make a proper classification. And so in our example, let's say we plot the dots, which are our data points, onto the graph. And as you can see here, we've also plotted a line that's going to serve as our initial guess hypothesis function, which is a pretty good guess so far. We only have one misclassified cookie. So how would we represent this in terms of thetas? Well, if you look at the math that I've done on the left, I basically turned this line from the equation of a line format to the format that we want, which is a dot product. And so in this case, we have theta 0 is equal to negative 0.5, theta 1 is equal to 1 over 976, and theta 2 is equal to 1 over 81. And so in this case, theta 0 is a regularization term. Theta 1 is correlated to the bake temperature, and theta 2 is correlated to the bake time. So now that we have the new hypothesis function, let's talk about how we're going to do the cost function. So we have a new cost function when it comes to logistic regression. And although it may look long, it's actually quite simple. So all the terms, j, m, h, x, y, mean the same things as they do in linear regression. But here you can see that we have this new function that we're going to use, log, which is the logarithm function. So what we're actually doing here is we're taking an average of the cost of all the points. That's why we divide by m at the very beginning. And we're summing from I equals 1 all the way to m, so over every data point. So here's how we can break down the cost function. So the summation has two parts. One that's multiplied by negative yi, and the other one that's multiplied by negative 1 minus yi. And so as we remember, yi can either be only 1 or 0. And so we place those terms there in order to cancel out a specific term based on what yi is equal to. So let's say yi is equal to 1. That means the first term is going to be an actual value, right? Which being when y is equal to 1, then the first part is only equal to negative log h theta of x. But the second part, because we're multiplying by 1 minus yi, which is equal to 0, it disappears. And the flip happens when yi is equal to 0. That means only the second part of the summation contributes to the cost. So we take the log of h theta of x in order to make the errors even larger. And having summed all these errors, we divide by m to get the average. And in this case, with the current data set, our j theta is equal to 0.96. And we want to make j theta closer to 0 as much as possible. And so here you can see two graphs kind of explaining or demonstrating what we're doing with the summation. And so for the first part, when yi is equal to 1, if our h theta of x is equal to 1, then there's 0 error. And if it's equal to 0, we have infinite error. And so this allows us to amplify the error based on what its value is. And remember, h theta of x can only be its value between 0 and 1 because we take the sigmoid function on it. So on the flip side, when yi is equal to 0, then the error output looks like this, where if our guess h theta of x is equal to 0, there's 0 cost, but if it's equal to 1, there's very large cost. And so here is just a chart to demo some of the data calculations that's going on to calculate this cost. So let's talk about gradient descent. So now that we have both the cost function and the hypothesis, how do we minimize it? Well, it turns out that our strategy doesn't change at all. If you do the math, you see that when we're trying to take, basically trying to minimize error, we get the same equation that we need to use to do gradient descent. And so everything here is the same as what we did in linear regression. So I'm just putting this up here for reference, but all you have to remember is how you did it in linear regression. And so after doing one round of gradient descent, we see that we should increase theta 1, which is correlated to a multiplier for bake time, and decrease theta 0 and theta 2, which is the regularization term and the bake temperature weights. So let's talk about one of the most important topics in machine learning, which is how to counter overfitting and underfitting. So when we try to model our data, we can run into two problems. If our model is too simple, then we won't be able to extract enough information from the data to make good predictions. But if it's too specific and complex, our predictions won't be able to generalize to new predictions. So, as we said before, we use machine learning to make predictions on data that we've never seen before. So we need to be able to have the right level of complexity and data in our model. And this is, again, one of the most important considerations when creating machine learning models. So let me give you some examples of what I mean by under and overfitting. So at the top, you can see some examples of a regression model. And so in the middle, we have a proper regression model that um, that models the data correctly. But if we have one that's too simple, let's say the one on the left, then even though it broadly models the data, the pattern that it tries to predict is too inflexible, and so it can't capture the pattern of the data properly. But on the right, we actually get the other problem, which is that we make our model so complex that it finds a way to squiggle and match the trend of every single training example that we give it. But when we try to give it a new data point, it will get it horribly off because the model is so wonky. And so if we look at the bottom, we can see examples of this in classification. So let's say we're trying to classify between two results. In the middle, we have a good result where we have the right trend, and even though we get some data points wrong, those we consider to be outliers, and we get the majority of them correct. So on the left, you can see this kind of separation model that we have here is too simple, so we make a lot of errors. And on the flip side, on the right, again, our model is too complex. So we draw these squiggly lines around the decision, the boundaries between the X's and the O's. But if we actually plot a new data point close to those two weird X's, we should predict an O, but we would predict an X instead because we have this small pocket of region where we consider it to be X, and so that will lead to incorrect predictions. And if you want to pause, this is just another example of underfitting and overfitting in a regression. So how do we tie this back to our cookie example? Well, for underfitting, an example is, imagine we only consider the bake time when we try to model our cookies, whether they're cooked or not. Without the information on bake temperature, our model would have lacked information to make good predictions, thereby underfitting. And if we're overfitting, imagine, in addition to considering bake time and temperature, we also trained our model to predict based on the position in the pan of the cookies and the number of chocolate chips in them. And so even though these variables don't help us predict in a broad sense if a cookie is cooked or not, it will help us predict more accurately whether a cookie was cooked or not from our training data. And so when we get new data, we'll make incorrect predictions when we have to consider new scenarios. So how do we solve underfitting and overfitting and get the right fit? So there are multiple strategies for either problem. If our model is underfitting, we have to increase the number of features in the model. So we can add, for example, the cookie dough ball size as a feature to the model, because that's relevant to whether a cookie is cooked or not, the size of the cookie. So we can also do things like adding polynomial features. So if somehow whether a cookie was cooked or not was correlated to the bake temperature squared, or the bake temperature times the bake time as a feature, we can add that to our model as a separate feature and have it train on that. We can increase the amount of time we train the model for, especially when we're doing something like gradient descent. And we can also increase the number of data points we train on to help cover more possible cases and prevent underfitting. So briefly, here's an example of polynomial terms. So this is the same classification example we had from before, but as you see on the right, what we're actually doing here is adding things like x1 squared times x2 as a feature in our data set. So of course we want to get the right balance, but this is essentially how you would add polynomial features. So there's some solutions to overfitting as well. If you notice your model's overfitting, you can decrease the number of features in the model. So, for example, removing the number of chocolate chips as a feature of the model because it's not relevant. We can decrease the amount of time we train the model for. And although this can be unintuitive, I can give you an example of how this works. So imagine the difference between learning the concepts from a textbook so that you can predict, given a new problem, how do you solve it. So that's proper learning. But there's a way to overfit it, which is if you simply memorize every word in the textbook. So doing this is counterproductive because if you're not learning the overall concepts and you're just given a word, you're able to predict the next word in the textbook, right? That's not useful when you're trying to tackle larger problems outside of the textbook. And so that's an example of overfitting. We can also increase the number of data points that we train on, and that helps give the model clear decision boundaries to help prevent overfitting. And we can use regularization. And so just on one note, as you can notice, we can solve overfitting and underfitting always by increasing the number of data points we train on. And so it's always better to have more quality data. Of course, this makes training slower, but with modern technology, that isn't a huge problem. So let's talk about regularization. I brought this term up in the past of this lecture when I talked about the theta zero term. So what does that actually do? So remember in our hypothesis function, we had a theta zero term that wasn't multiplied with the bake temperature nor the bake time. So the reason we add this is so that we can prevent overfitting, as we said previously. And so if you notice in our hypothesis function, theta transpose of x, in this case, is equal to theta 0 plus theta 1 times bake temperature plus theta 2 times bake time. And so there's actually, for x, an x0, x1, and x2 that I haven't told you about, just because I was keeping the explanation simple. But in this case, our x0 would always be 1, because we always want to multiply x0 to give, with theta 0 to give theta 0. And so our x1 is the bake temperature, and our x2 is the bake time. And so for every data point, we actually add an x0 that's always equal to 1 in order to account for this regularization term when we do the dot product. Because as you know, dot product is equal to theta 0 times x0 plus theta 1 times x1 plus theta 2 times x2. So why is it that we have this theta 0 term? Well, it's because you can think of the theta 0 term in a similar way to adding a y-intercept b in the equation of the line y equals mx plus b. So we add the regularization term to the hypothesis function to better model the data. Because as you can imagine, if you're trying to draw equations of a line and you didn't have that b term, then your line would always have to go through the origin, and that would mean you wouldn't be able to properly draw lines or model data. And so in general, what the regularization term does is it helps us, conceptually, we add like a y-intercept, quote unquote, but it also helps us to reduce the importance of each parameter theta to prevent overfitting. So if we want to prevent overfitting more strongly, what we can do is increase theta 0 as a setting in our model, and then relearn theta 1 and theta 2 according to that theta 0. So let's talk about the last topic of this lecture, which is feature normalization. So as you can see from the data, the bake temperature had a much larger range of values than the bake time, on an order of magnitude. And so when computer scientists did machine learning, they basically noticed that the gradient descent descends more quickly on small ranges and ranges that are similar to each other. And so between features, we want to have the features actually fit into the same range as each other. And so that's why we use a concept called feature normalization in order to do that. And so feature normalization is just a combination of two techniques, feature scaling and mean normalization. So let's go into each of those. So feature scaling simply means that we divide the data for a feature by its range so that the new range is just equal to 1. So in this example, for each bake time value, we divide by 12 to get a new range of 1, because the range of the bake time values is equal to 12. And so as you can see on the right, we have a chart here which reflects the new values that we put into our model. Mean normalization simply means that we subtract the mean of the data so that the new data has an average of 0. And so in this case, we subtract 8.61 from the bake time to get a new average of 0. So the values on the right, we have some that are negative, some that are positive, but all of them average together have a mean of 0. So feature normalization simply means we combine both approaches. So first, we subtract the mean. Then, we divide by the range. This makes our data normalized, so that it has a range of 1 and an average of 0. And so we apply this to every single feature in our data set. So in this case, bake time and bake temperature. And now our model can converge much more quickly. And so just a general policy, you can imagine feature normalization as a function where we take every x, subtract the mean, and divide by the range. Simple. And so on the right, we can see a chart where our feature normalized data is on the rightmost column. So just to review all that we've covered today, we've covered a new hypothesis function that uses a dot product and the sigmoid function in order to fit the input from negative infinity to a range of 0 to 1. We have a cost function that basically allows us to evaluate, how wrong our model is compared to the binary outputs that we expect. And then we have the same old gradient descent equation that we use from linear regression. We talked about how we use regularization in order to prevent underfitting and overfitting to get a better general model. And we talked about how we can use feature normalization in order to speed up gradient descent. So yeah, that's all the content for this unit. Our first assignment is going to focus around university admissions, which I'm sure some of you have already been thinking about. So in this assignment, we're going to implement a logistic regression model with the provided Jupyter notebook file. While most of the code is done for you, you'll still have to fill in the equations above using Python and NumPy code. Once you've tested your code and are finished, you upload your completed file. And if you ever get stuck, please ask on the discussion forums and what your error is. At the end, you'll have created a basic machine learning model that can estimate whether a student gets into university based on 2 test scores. And of course, this is not how it works in real life, but it gives us a nice way to try and tackle logistic regression for the first time. Alright, well, thank you very much for listening, and hope you have a great time learning. Bye-bye.